Quantum computers are about to change everything. This is the third video in my Quantum AI series that concludes in a 15-year trend forecast for the AI stock sector. However, the whole of this analysis has already first been made available to patrons who support my work. So for immediate first access to all of my analysis and trend forecasts, then do consider becoming a patron by supporting my work for just $3 per month. So, think Moore's law is dead? Clearly those of that opinion do not understand quantum computing. Though I don't blame them, because 5 years ago neither did I. I just knew that they promised a jump in processing power beyond that of classical computers. Instead, it's more akin to an acceleration in compute power when quantum computers start leaving the labs and entering the workplace, likely during this decade. Which is why I think everyone needs to take the time to understand what quantum computers are and how they work, for only then one can begin to comprehend the real world consequences of what AI quantum computing future heralds for all of us. So take the time to understand three key aspects of quantum computing: superposition, entanglement, and interference, towards which there are already several hundreds of YouTube videos, of which you will likely need to watch several dozens to comprehend the mind-numbing nature of quantum computing, which is necessary to be able to make the leap towards what it will mean for when AI merges with quantum computing to become quantum AI. Whilst today's quantum computers, despite their promise of harnessing the processing power of superposition and entanglement towards calculating all possible solutions to a problem at the same time and then collapsing into the most probable best solution, nevertheless are primitive in the sense they resemble classical computing of the 1960s and 70s, one of huge room-sized delicate machines that required fine-tuned conditions to work at temperatures near absolute zero, where entangled states can only exist for mere fractions of a second. Still, it's enough to send shockwaves through the establishment, for it heralds the end of encryption as we know it. Crypto investors take note. Today's trend in quantum computing is towards creating quantum computers with an ever greater number of qubits. With the chip with the most qubits on it goes to Google with its 72-qubit processor, whilst the computer with the most qubits in total goes to a Canadian company, D-Wave, with a 2,000 qubits machine that apparently sells for $15 million. However, the truth of the matter is that these machines are very delicate, operating near absolute zero, where most of those oft-publicized qubits are used in error correction, as today's quantum computers tend to generate millions of errors per hour, compared to, say, your desktop computer that perhaps generates one error per month that results in a crash, and even then it's likely due to the operating system rather than the processor. Thus, from what I can see, the actual number of working qubit systems of today's quantum computers tends to vary between 4 and 8, as the rest are used for error correction, spreading the quantum states of one qubit amongst many physical qubits. So we are at the very early stages of the quantum computing megatrend, with only a couple of algorithms shown to run faster on quantum computers than classical computers, such as Grover's SAW algorithm. In fact, the coronavirus illustrates the point that despite quantum computers being ideal for modeling of the virus, are not being used to do so because the technology has not reached a point where it is capable of delivering that which it promises. Widespread practical use of quantum computers requires four major breakthroughs. Firstly, to be able to operate at temperatures far above absolute zero, at temperatures achievable in commercial settings without the need for liquid nitrogen or helium, perhaps no colder than -30. Secondly, much better error correction so that more qubits can be used for superposition rather than error correction. Thirdly, greater stability in being able to hold superposition states for longer than mere fractions of a second, so that more sophisticated algorithms can be run. And fourthly, better methods for setting and holding the quantum states than magnetic fields. These breakthroughs will be achieved through a process of innovation to take place over the next 15 years that will take quantum computers out of the labs and into commerce and industry. For we have already seen it happen before with classical computers that have gone from CPUs with a couple of thousand transistors in the early 1970s to today's retail high-end desktop processors, such as the 40 billion transistor Threadripper 3990X. IBM has already made available its quantum computers via the cloud for anyone to access and tinker with, as the tech giant is busy constructing a library of functions that programmers can call upon, understanding that who gets there first tends to win, i.e. the library of functions, circuits, are likely to prove far more valuable than the actual hardware, which today is primitive and soon likely to become obsolete. It's the libraries of functions that will drive quantum computing because they can be run on either quantum or classical computers, or more probably a mixture of both, with programmers using traditional programming languages such as Python. I.e. a classical computer runs part of the algorithm on a quantum computers, given the unstable nature towards which artificial intelligence is well suited towards managing the many passes it will take to arrive at a high probability best solution. And IBM is not alone in developing quantum computer library functions, as the race is on to win the quantum functions platform war. Google, Microsoft, and more than a dozen less known corporations are already busy beavering away designing circuits that interface as functions for programmers to utilize for when quantum computers become more reliable. The current most powerful quantum computer is D-Wave's 2000 qubit machine. But how many of the qubits can it actually reliably deploy towards problem solving rather than error correction? Probably no more than a dozen, and even then only for a fraction of a second. So it's going to take a while, perhaps until we get a 100,000 qubit machine, where most, maybe 85% of the qubits are used for error correction. That may just mark the breakout point for when the functions libraries can start to be reliably deployed. Maybe starting in 6 or so years' time, which I'm sure will be accompanied with much public interest and media hype in quantum computing stocks. So we have two megatrends. The AI megatrend of ever more sophisticated machine learning algorithms running on wholly classical computers, taking jobs away from humans as more laws delivers ever more powerful processors and GPUs. And the quantum computing megatrend, one of ever-expanding number of qubits machines, with both trends chugging along on their exponential curves towards. Find out in my next video. And this video is excerpted from my extensive analysis that concludes in a detailed 15-year trend forecast for AI stocks that has first been made available to patrons who support my work. So, for immediate first access to all of my analysis and trend forecasts, then do consider becoming a patron by supporting my work for just $3 per month. And do remember to subscribe to this YouTube channel for the next video in this series, though it's unlikely that all of my extensive analysis will be converted into videos, which is another reason to become a patron by supporting my work for just $3 per month.